And as a reward for that, before I start with my talk, here are some pictures. So on the left, that's my lab, just a snapshot at one point of people in my lab. On in the middle, any guess what this is? Just to give you a hint, and my program is called Climate Change Science and Policy in an Emerging Economy. So I run that pretty much every summer in non-pandemic years, and so that's just a hint. But in the middle, anybody recognize this picture? Yeah? Close. So this is Mount Chomolungma in modern day Nepal, which for some weird reason is named after that guy called Everest. So we sometimes call it Mount Everest. All right, and then on the right, can anybody, not you, Dion, can anybody identify that? So I told you emerging economies, so we went to India and Nepal once, and then on the right, that's in Bali, Indonesia. That's the goddess of learning, Saraswati. All right, so we have been to many places like this, including, other than these places like Brazil, Peru, Tanzania. I'd invite all of you at some point to consider joining us. All right, what I'll do today is quickly go through some motivational slides, if you will. Many of the things I say, I'll try to cover things that are broader than our own work, but unfortunately we sometimes get towards those are the things that we know best. So I'll get towards some things that we have done, but I'll not be able to cover, of course, everything that we have done either. So especially I'll take a view of climate resilience here, which is a longer term issue that that has been called the defining challenge of our age by the United Nations. There are many other things that relate to climate, such as handling emergencies, agricultural remote sensing, short-term floods, and things of that nature, which I'll not talk here today, but we have done significant work with AI and machine learning in these areas: remote sensing, emergency management, etc., and crop mapping, and the community has. But then that does relate in a sense to climate. So if climate change is growing to be more and more of a problem, we need to do something about it. If there are more emergencies, then we need to build, besides longer term capabilities, we need to build short term capabilities to be able to handle those emergencies. Today I'll not talk too much about that. Before I start, also, by the way, we have been very well funded, I would say, by organizations like NSF, NASA, DOE, DHS, Department of Defense, national labs, Pacific Northwest National Lab, Oak Ridge National Lab, and I happen to have a joint appointment at PNNL, Pacific Northwest National Lab. All right, so first let me talk about what is being called the global weirding challenge. Some people have been calling it global weirding. It seems that global warming is no longer conveying what it really means. Yes, there is global warming, but things are changing significantly and causing us to either adapt or mitigate or face dire consequences. So things are growing a bit weird. I'll talk a little bit, just give you one example of what that means. For example, in the context of extremes and stresses. I have exactly 42 slides, by the way, but that's just incidental. All right, so global weirding. Here is one example with temperature extremes. So on the left, this is a paper in the Proceedings of National Academies from 2009, long back, which talked about heat waves. So higher trends, higher than what we thought then, higher trends in heat waves and regional warming, but larger uncertainty and more geographic variability than what we thought. And remember, this is 2009. This has been a while. I was at the Oak Ridge National Lab then. I led that particular work. There is a whole community, of course, working on temperature extremes. This is just one example. in 2011, two of my former PhD students, Evan Kodra and Karsten Steinhauser, they came up with this paper in Geophysical Research Letters, which was sort of a reverse, in a sense, of that heat wave paper, which said persisting cold snaps in a warming environment. So what that means is the dispute is not with the fact that the planet is warming. The point is that despite the overall trend in warming, which is an average trend, the tails of the distribution do not necessarily exactly follow the average. So what is happening in terms of cold extremes, for example, the frequency of cold extremes, climate, remember, is average weather. It's average over several years. So we are talking in that sense, statistical sense. The frequency of cold extremes are decreasing and are expected to decrease based on models and observations. But the extremes that do occur, the cold extremes that do occur, might be as severe and as long lasting, and sometimes more so, because of various geophysical reasons than what we are used to see. Here in Boston, I don't think I need to convince anybody about that. But that's interesting. I mean, in fact, at that point, this was 2011, it was so interesting and sort of, non-intuitive that the journal Nature took this, they ran a research highlight on that saying, cold spells in a warm world. Right? And there has been a lot of work now, after this is 2011, so more than a decade old, a lot of work now on explaining why, what that, starting with, Arctic cold snaps, polar vortex, things that we sometimes hear on weather channels. But point is, those are the two sides of the story, and that's why, again, global weirding, it's not just global warming, yes, we are not doubting that, but we are saying, okay, we know that, now what? Well, extremes on the heat wave side and cold extreme side. Just looking at temperature extremes. Weirding. All right, what does that mean though? So here is Boston, New England. On the left, warm. On the right, cold. So, and this is fairly new, so or recent. August 11, 2022 on the left, February 4, 2023 on the right. So what you see on the left is record hottest 30-day stretch in history. And these stretches have sometimes much more significance than just one hot extreme. But so that's from CBS News Boston. And on the right, historic Arctic outbreak crushes records in New England. So, in some of us who are working in climate science, there is this thing about, none of us are too happy because, if a doctor recommends something and not as much is done about it, the doctor is usually not happy. So that's another side of the story. But in terms of our Nostradamus-like capability, it's not that difficult. So we see these kind of trends, right? And so, look, this is what is happening, and this is happening across the world. Here, this example is with Boston and New England. Now let's move to the great state of Texas. Not to mess with Texas in any way, but again, heat waves on the left, cold snaps on the right. Texas is power grid. And you know that Texas has its own power grid, pretty much. Not weatherized. Heat waves, they are down, cold snaps, they are down. I am not messing with the great state anyway. It's the weather, and they will mess with it unless you prepare your engineered systems a bit more carefully. Just the fact that, you don't have to even call it climate, for heaven's sake. Just call it power, uninterrupted power supply, right? One of the major lifelines of today. All right. Now, so sometimes we talk about in these kind of, things that we try to do, we talk about participatory modeling, getting stakeholders together. There are some silent stakeholders who cannot speak human languages. I sometimes think some of them are smarter than we are, but that's just me. But point is that they are suffering too. Again, heat waves on the left, cold snaps on the right. So if you look at, this is off the Pacific coast, and they're talking about salmon. So ecosystems and species dying off. Many of us are aware, especially some of us who are seafood fans, that the whole lobster industry has moved from Boston towards Maine. And now that Northeastern has this Rue Institute in Maine and the strong connection with Maine, especially the AI Institute, now what we are worried about is that that lobster will move from Maine off to Canada. Nothing against Canada, but and we don't want these species to die. I mean, I don't want to trivialize it. It's not just, there are so many species and some of them we might lose forever. That's from heat waves on the left. On the right, cold snaps. So again, this is like saying the average warming is there. On an average, let's say, just to give an example, on an average, the undergraduate student population of Northeastern is growing, I don't know, if you call it smarter. Let's just say the test scores are increasing. I don't know if there is an easy way to talk about who is smart and who is not. Let's just say the test score, that's a quantitative metric, test scores are increasing. That's an average thing. But that doesn't mean that if you look at the top 10% test scores, bottom 10%, they may have a very different trend compared to the average. So that's just basically what they're saying, that, well, when you talk about the extremes, when you talk about the tails, they may behave differently than the average, and that behavior in another paper we showed, that behavior may be asymmetric. It's not the entire distribution is shifted. All right, talking about emergency management. Again, heat waves on the left, cold snaps on the right. Heat waves in countries like this, the world's most developed countries, and which are usually in temperate or colder zones. We have a lot of resources, and I would say it's a national shame that heat waves cause a lot of deaths, especially of people who are the most vulnerable. Sometimes it's kids, but oftentimes it's senior citizens, single family households, low income groups, right? And just look there, heat waves, the fatalities more than any other thing, including floods, tornadoes, hurricanes, in terms of human deaths, one of the most, right? So clearly something needs to be done in terms of reacting to those, getting prepared to heat hazards and things like that. Boston has been doing something, it's called Climate Ready Boston. The town of Brookline has been doing something, and now there are many other towns and cities in this country which have started to do various things. And then cold snaps. Well, again, cold snaps do not cause as much death, but they do cause comorbidity, and of course, as we all know, they cause a lot of discomfort. So I've been trying to show you what global weirding, in a sense, why we call it global weirding. But of course, this is not just temperature. We have done work, others have done work which show that this kind of thing is prevalent from heavy precipitation and floods to droughts of different types, to wildfires, hurricanes. Temperature is, by the way, one of those variables which are more credibly projected. But we have seen this kind of trend in many places. So here, for example, on the bottom left, what I'm showing from an earlier paper is these are return periods of heavy storms, things like 100-year levels. And why are these 100-year storms, the storms that you'd usually expect once every 100 years? Why are this important? Because we design based on that. Design our hydraulic infrastructures based on that. Design operational principles based on that. And the kind of things that we see here is that, what used to be, let's say in 2000 here, a 30-year extreme happens once every 30 years. By the end of this century, we are looking at those becoming 5 to 10-year extremes. So now our design curves change on us. Something needs to happen. And in fact, observed trends show an even higher trend than what models show. So this is just an example, but we have looked at, and as I was saying, others have looked at. I gave examples with temperature, but that's not the only thing. Not the only variable where we see global weirding. And there'll be many occasions here when I'll sort of blow my own trumpet. This is one. So, which is, this was a very recent article in News. And this is, so September 2022, and they have published a few like that. This was called Global Weirding, Humans Have Caused Chaos on Earth. And I may have a little bit to do with that exact title. But they were saying that, look, here are the kind of things that's happening, and this was, an interesting article. Actually, I did have something to do with this title. So what I wanted to say here is exactly what I was trying to go through here, that we call these global weirding because it's not just that heat waves are getting hotter, cold snaps are persisting, heavy precipitation is getting heavier, and so on. And the impacts can be across sectors, ecosystems, coastal processes, urban lifelines, water, energy, food nexus. The other thing that's happening, and this is interesting, and many of you here are AI, this is the Experiential AI Summit, and I would love for you to come and contribute here, is it's not just that things are changing in the means, okay, warming. It's that fluctuations are changing. Uncertainties are changing. And if you think of chaos theory, underlying predictability, some of you may be very familiar with nonlinear dynamics and chaos theory, some of you not so much. If you still remember your Jurassic Park, think about chaos theory. From there is the maths of chaos theory, not the chaos that we get when we let kindergarten kids be there without a teacher. So it's things like, extreme sensitivity to initial conditions. It's things like following some sort of order in the midst of disorder. It's that butterfly effect. All those kind of things. And those kind of things seem to be increasing. We seem to be getting towards the state where the inherent uncertainties, systemic variability and uncertainty and fluctuations, they're different things slightly, but they sometimes influence one another. Those things seem to be increasing, and this limits of predictabilities itself seems to be changing in some cases. So how do we design? We still have to be resilient. We cannot say, okay, fine, we cannot predict, that's it. Let's look at another problem. Sometimes in AI kind of fields, we tend to do that. Okay, let's look at a problem when you solve. Not just AI, we tend to do that in many fields in academia. I can solve it, let me look at that. But hey, even if I cannot solve it, we have to look at this problem. So what is it that we can do? And there could be interesting things that could come out of this. So now let me take you through another journey, not in climate, but ozone hole, which is a bit different, but still talks about atmospheric processes, where I have been partially involved. So I go to, they call me to these United Nations panels as a review panelist and so on. So I happen to see that, and agrees with some background that I had earlier. That's about it. But here I'll talk about something else. I'll still talk about climate. I'll come to it. But the point I'm trying to understand here and try to discuss with you, if you will, is can science really inform globally coordinated action, or is it just hopeless? So let's look at ozone hole, and I apologize for the busy slides. So here there was a paper that came out in the journal Nature, which is a very high impact journal, sometimes called the best journal in interdisciplinary scientific areas, etc. This paper came in 1974. It talked about the science of chlorofluorocarbons, things that were used in refrigerants, messing up with the ozone layer and causing the ozone hole problem. 1974. Mario Molina right here, he was a grad student, and Sherwood Rowland was the advisor. And then in 1987, the Montreal Protocol was finalized. So that's 14 years it took for the world to come together, but it's still okay. We are talking about the ozone hole closing and all that. I'd take 14 years for action to no action. I mean, it's all relative here. But the Montreal Protocol happened. And then 7 years later, there was the Nobel Prize, the first Nobel Prize in any of these kind of areas, geoscience, atmospheric science, etc. So they were recognized. I was privileged to take one course which was team taught, and one of the professors was Professor Molina, extremely talented scientist. Of course, I don't need to say that, the Nobel Committee already said that. As a teacher, then coming back though, now 2020, the Kigali Amendment was signed off, which is so it's a continuing thing. It exceeds 100 ratifications, and lo and behold, September 2022, our Senate ratified the pact as well. I mean, the US was part of the Montreal Protocol, but has been a bit slow, but still, even the US signed that pact. And one interesting thing on the bottom left is, if this Kigali Pact is successfully implemented, it would probably lead to more impacts on reducing global warming, because some of those gases, chlorofluorocarbons, are also greenhouse gases. So it will lead to more impacts than all the conference of parties and the private jets that we hear. I'm sorry, but that's just the feeling that I have. And this is not a feeling, this is true. All right, so that's that. Now let's come to climate. Situation there is interesting. So the first Nobel Prize in climate-related areas was in 2007. It was awarded for peace to former Vice President Al Gore and the Intergovernmental Panel on Climate Change, which is the job of the UN IPCC. Is they also comprise scientists, but their job is to assess the science, not to do the science, as part of the IPCC. As individual scientists, they of course do science. Anyway, so they got that. If you think of adaptation and impacts, sometimes you think of economics as one of the major factors. That Nobel Prize was in 2018. And I'm not suggesting that Nobel Prizes are the only measures. I'm just using that as one measure. And then 2021, finally, the Science Nobel Prize. This is the Physics Nobel Prize, awarded to Shiguro Manabe for climate simulations, to Klaus Hasselmann for what is called optimal fingerprinting, using simulations and observations with what we could call data sciences, if you want to call it, whatever you want to call it. These days we seem to call everything machine learning. I wouldn't call that machine learning, but machine learning has been used in those areas, not by Professor Hasselmann, but by others. And then Giorgio Parisi, who is a complex systems scientist and has published in climate and ecology, but the focus has been on complex systems more generally. So it's almost the chronology is reversed. I would say you first do the fundamental science, understand it, natural sciences, and then say, okay, here's the impact of that science, and here's the economics that follows, and then the Peace Prize comes up. Yes, you see that it's a bit reversed. And here is Klaus Hasselmann saying that I hope that young people succeed where we scientists have not. It's interesting, right? I have Greta's face here just to highlight that. There are, of course, nuanced views which we can have about, should Greta run, what needs to be done in climate systems. Fine, we can talk about that all day. But the point is that nobody can deny that she's making these things visible, and that has to be done. And look what is happening. So as earlier I showed in the ozone hole problem, that here is what is being done, and even the US is on board, etc. But here climate pledges are falling short, and a chaotic future looks more like reality. This chaos is not mathematical chaos. This chaos is that chaos I was talking about when you leave undergraduate kindergarten kids on their own without the teacher. All right. Now, to be a bit fair though, the problem is much more complex. So if you think of climate problem on the left, it's a combination of things. It's, of course, policy myopia, it's financial disincentives that are built in terms of climate preparedness, which leads to these outdated best practices, engineering stagnation. So it's a vicious cycle. Our thesis, at least some of our thesis, has been that it doesn't take a whole lot of effort to transform that vicious cycle into a virtuous cycle. what is probably needed are financial incentives and transformative science to start the wheel. Then you need all of those, but at least to start the wheel. So I'm not a pessimist by any means, but we need to do this soon. And the thing that here is this paper by some group in Nature. It's a perspective article which shows the many different types of uncertainty. So on the right, for example, it shows how that uncertainty curve is spreading from climate to weather scale to physical impact and to economic damages. We are talking about a very complex system here. And potentially the ozone hole problem is a little bit less complex, if I can say that. I mean, of course, people can argue with that. But here it's much more complex. So, okay, so that's there. And the other thing is countries, regions, even cities, they would first look at their own interests rather than all of us joining hands and saying we kumbaya. Should we do that? I mean, sometimes we overdo that in the sense that, we say, yes, I mean, we have to be able to do something, we have to be grown up, right? And we have to be adults and not just think about, not just be sentimental and empathetic. Okay, grow up, right? And just for that feeling, you don't have to be so self-centered in a sense that you are harming not just yourself but everybody else. There is some game theoretic element here, right? Okay, so grow up. So, but the point is, this was climate change war game, a role-playing exercise. In this case, it was done with real players who actually go and talk about these at these conference of parties. These are people who mostly do not go on private jets but do the actual work. So the Center for a New American Security got many of them together. I was at Oak Ridge Lab then. They asked us to produce some figures and visuals. We did. And they called us there, and I was part of that team. At Oak Ridge, I led a small team of students and postdocs to be able to do that. And these words have been used by others, not us, not our team at Oak Ridge, but over there. So adaptation has been called managing the unavoidable. Mitigation has been called avoiding the unmanageable. And if you think of, when you think of how countries or regions react, you think of resources, hazard, population, and then emissions, roughly in that order. And then how all of these connect to each other, and discussions around things like environmental refugees, what should be done. So there is that element. It's a global problem, but regions react based on their self-interest. So a lot of uncertainty, and regions react based on that. All right, so with that introduction, let me now come again. This is an experiential AI seminar, and I am fully aware of that. So let me come to some solutions. There's a whole bunch of solutions that we need to build, but here I'm going to only focus on the things that relate a little bit more to artificial intelligence, machine learning, but I'll come to that. So going back to that ozone hole thing, on the left, that's the 1995 chemistry Nobel laureates, two of them, there are three of them. This is the graduate student then, later Professor Mario Molina and Sherwood Rowland, who had that Nature paper in 1974, and that is their lab. Those are their instruments, those are the things with which, and those things have obviously improved, but that's how those kind of setups look. For some of us in climate, the setups look a bit different. So this is about the same time, 1970s, one of the Nobel laureates here in physics in 2021, whom I showed, this Nobel laureate was for Earth system or climate modeling and simulations. He had a computer. That computer probably had 1,000, if even that, of the power that's there on my cell phone today. But he was doing some of those most advanced simulations then. That is the corresponding lab instrument, lab equipment, if you will, that is needed in these areas for simulations. And even today that continues. So when we even think about, to what extent are we doing curiosity-driven research versus what is called mission-driven research? So at the top, that is the MGHPCC, the Mass Green High Performance Computing Center, which on the right, as you see, is shared by various universities in this region. And it's fairly powerful. But compared to this one, which is the top 500 list at Oak Ridge National Lab, at various points, they have the world's highest, fastest supercomputers. That's nothing. And if you think about the largest climate simulations right now, the major global simulations, they are called Earth system models. They take significant time on these largest supercomputers. So that is the instrument. And then what are the challenges again? So if we think about natural systems, I talked about chaos, I talked about complexity a little bit. Now let's talk about how these manifest themselves in natural, human engineered, and social systems. And again, they are not independent, they're tightly coupled, of course, as we know. Natural systems such as Earth systems are impacted by human activity, and that's why we're talking about it. So we know all of those kind of things, but still, to the extent that they can be somewhat looked at, somewhat compartmentalized. So if you think about natural systems, that's on the left, climate systems, we talk about trends and natural variability, we talk about chaos, spatiotemporal chaos, complexity, and that's where things like physics-guided, uncertainty-aware, machine learning models, which are aware of space and time. I mean, you might ask me, well, in computer vision, we are doing computer vision, we are aware of space and time. Yes, but there's need to be a little bit more aware here in the sense of the kind of correlations that occur here, and in dynamical systems, the kind of long-range dependence that we see, the kind of things we see in time and space, the complexity. So you have to be aware of that and then build some of these models. You have to be aware a bit of the physics, different variables guiding, these kind of, let's say, rainfall extremes and so on. So that's one. Then we talk about engineered systems and what are called cascading failures. This happens, by the way, in ecosystems as well, and in food web, for example. But here, if you think of engineered systems such as power grid, communication systems, transportation systems, water distribution systems, not only are they tightly coupled to each other, and they're tightly coupled sometimes across wide areas in space-time. If you think of the airspace system, global system. Now, some of these things are tightly coupled because either we wanted them that way or because they self-organize that, because there is an advantage to that. We get mutual support, mutual help from that. So I can take a train from here to Boston Logan, and then from Boston Logan, I can take a flight to Singapore via another airport, potentially, but I can. We want that kind of flexibility. So there are things these things are highly interconnected and have become more interconnected, are becoming even more interconnected because we want it that way. But what that also means is that vulnerabilities are shared, right? So if there is, given that we are seeing more and more extremes from natural systems, I told you about heat waves, cold snaps, floods, droughts, hurricanes, you name it, tornadoes, but any of these extremes, if they cause a damage at one single point, that damage might percolate across the system, let's say power grid, and then cascade across multiple systems. Power grid failure will cause failure in signals and systems, hence transportation failures in water pumps, hence water distribution networks, etc. So, and communications, of course. So that's one thing. And here, the kind of AI machine learning tools that could be very useful are probabilistic graphical models. Sometimes, one type of those are what is called complex networks, and Northeastern University, as you know, is very well known, probably the world's #1 in network science, so that is there. And also, in general, if you sort of expand on that, probabilistic graphical models which deal with uncertainties, causal flows, those kind of, that's the AI. So in one case, it's spatiotemporal machine learning and computer vision. In another case, it's graphical models and machine learning potentially on those graphical. But then on the right, now we have this other challenge, which is people. Those specific things, right? I mean, but people. Well, we cannot leave out people out of the equation. And there we have tragedy of the commons. So I own this cell phone and I will take care of it. I don't own the air. I don't own the public transport, MBTA, the T, but all of us own it. Who takes care of it? Right? None of us do, all of us do. Tragedy of the commons. It's owned by the commons. Tragedy is that who will take care of that? And then, of course, there are financial disincentive structures built in. I'll talk about one other Nobel laureate. I have a name somewhere here. The first woman economics Nobel laureate was somebody called Elinor Ostrom. And she had this interesting idea of, in complex systems. So each of these systems, you're talking about complexity in different ways. Here we're talking about complex social systems. In complex systems, what is the best way to manage these systems? And she talked about polycentric management. Very interesting ideas. And, some of those ideas and other ideas have now morphed towards things like stakeholder-centric modeling, participatory modeling, etc. Where could AI come in here? Agent-based models, avatars, right? So in each of these areas, natural systems, engineered systems, social systems, we have different flavors of AI, which are already useful, could be immediately useful. Of course, when I say that, I fully realize that all of you will come up with something else, which is this also is useful, absolutely. But just to give you an idea of the kinds of things that could be useful in each of these natural, engineered, human systems. Okay. All right. Microsoft solves everything. Originally, it was Google. There was a time I remember my nephew gave me this T-shirt that said, maybe I may have given him too much words of wisdom. So he gave me this T-shirt which said, Google doesn't know everything. Come to me, with this yogi sitting like this. But these days, it's interesting. So now it's Microsoft, and with ChatGPT and so on, and which all of you are, of course, aware. This is not ChatGPT per se, but there are some similarities with the kind of models. This is also a deep learning model. They call it Climax. And as the title said, the first foundation model. Some of you are probably aware with foundation models in AI. How much time do you have?
Love to open up a Q&A. We've got some great questions.
Okay.
Yeah.
All right. So maybe give me a couple of minutes. So Climax, and we have, they solve several things with deep learning. Now, remember, when they say they solve several things with deep learning, they have to actually use simulations and models. So here we are not talking about getting rid of simulations, because that's what they use for their training. But they also use other things for training. And they say that because of the way these training things work, the self-supervised learning, the transfer learning, you are more aware of it. Many of you are more aware of it than I can explain here. Some of you are not, that's fine. But just take a look at, this is from Microsoft Research Automated Systems and Robotics Group. This is very new, by the way. And they are saying, okay, now we can solve many of these problems once we train with simulations. This deep learning approach learns this and then can solve certain problems which directly those simulations cannot solve. That's the claim. It's a very recent claim, needs to be evaluated. We'll talk about that. The other place, and I'll probably end here, the other place is, in terms of talking about agent-based systems, graphical models, this, I'm not sure if a whole lot of work has been done in climate per se. There are people building stakeholder-centric models, participatory modeling, but in terms of bringing in social systems, human systems together. But what this shows is, this is a model from epidemiology. And we have, at Northeastern, we have one which has been used by governments in the US and worldwide. It's called GLEAM by Professor Alex Vespignani and Steam. So this have a concept of networks in terms of transportation networks. This have a concept of spread of infectious disease, how people connect with each other. So again, a combination of techno-social systems, if you will. Sometimes I think with this techno-social ideas, maybe the engineering and social sciences colleges should merge with each other. Please don't say that I said that to any of those two Ds. But a lot of modeling from agent-based modeling to AI on graphs that's happening. So far I have covered half of the 42 slides. So I've only given you half of the wisdom. But I think it's a good point to end. I'll be happy to share the slides, by the way, Liz, if you want to share with. If you want to share all these slides, and please go to our website, which is, I'll just take you back there, which is sdslab.io. SDS is Sustainability and Data Sciences Lab. sdslab.io, and I have more expanded versions of some of these talks. For example, at the SC Supercomputing Conference or the Environmetrics Conference, you'll see that on the news slide on the right. I will end though with some of this last slide, which is that some of my students and postdocs who have contributed to what I showed here or was about to show here, which I can share the slides with you. The premise is what is in the center. No ChatGPT in the foreseeable future can accomplish what they have collectively accomplished. With that, Liz, I'm open for questions.
Thank you so much. All right, round of applause. Fantastic.
Fascinating topic, and I think it's good to have more than one session with you. It's like a mini series. It's like the trend today, so we can put it in Netflix also later. So we have one question in the Q&A. So we have two now. So the first one is climate change, and no pun intended, is always a hot topic. How do you convince naysayers that AI can predict the whims of Mother Nature and prove them wrong?
All right, Auroop, did you hear the question? I will repeat it. Climate change is, no pun intended, always a hot topic. How do you convince naysayers that AI can predict the whims of Mother Nature and prove them wrong?
Prove them wrong? Mm-hmm. Oh. So there are a couple of ways to look at it. We cannot potentially go to each and every naysayer and make it our job to try to convince everyone. That's not feasible. But as long as we convince everybody and convince ourselves that this is a risk management problem, I think we can get there. So going back to this ozone hole issue, one of the main decision points was taken when from this country, and for better or worse, policies that this country decides the world often follows or has to follow, whatever it might be. But the president at that point of this country was President Ronald Reagan, Republican president. Those were different times, I admit, but given that, so the point was that it was not that everybody was convinced that this will happen or there were no naysayers about the ozone hole and, my refrigerant and ozone hole, really? And then there were the industry sector, some of whom build those refrigerants. But two things happened. First of all, from the industry side, they said there are alternatives. And I know some of you here are looking at alternatives such as what solar can do for us, just as an example. But the other side is, so there was that, but the other side is policymakers said all the way up to President Ronald Reagan, let's sit together. What if these scientists are right? We don't have to agree that they are right. What if these scientists are right? That becomes a major risk for all of us. Let's treat this as a risk management problem. If somebody tells me that, a person or an organization, whether it's a rogue nation, a superpower, or a smaller, group, bad guys, they might drop a nuclear bomb, dirty bomb, whatever on us. Will I ask for, can you specifically prove with what percent probability that is true? If it has high enough probability, I'll try to make myself resilient to that. And that is, I think, all that needs to happen here. And the analogy is with this ozone hole. I don't think of my job as having to go to each and every person and convince him. That being said, sorry, there is somebody, I have a friend, her name is Catherine Hayhoe. very well-known climate scientist, but also known as a climate communicator. So her husband is a pastor, Christian evangelical pastor. They used to live, I think they still are, in Texas. And she goes to that community and says, hey, you don't have to leave aside your belief system to appreciate why climate change is a problem and that something needs to be done about it. So there are some of us who are good at that who are also doing that. So it's a combination to answer that question. Liz?
Fantastic. All right, we have about 5 minutes left. Does anybody in the room have a question? And Auroop, if you could repeat the question for our virtual attendees, that would be great. We'll open it up to the people that are here.
You usually have this affected audience stunt.
Hi, are there some, I guess for lack of a better word, orphan issues that you worry about? And by orphan, I mean issues that are immediate, dangerous, and not getting attention. So I'm thinking about things like asphalt. People say you could try to make a street or something so hot. And I was with my neighbor a couple of years ago, and her dog was screaming. She picked them up because the surface was so hot. And she tested the surface of the asphalt. And she put her hand. So I looked it up. Asphalt warps at 125 degrees. That's in the lab. With direct sun, it's going to warp earlier. With a heavy load on an interstate highway, several tons, it's going to warp sooner, and the friction from the tires will generate more heat. I looked further and I found instances of warping in Australia, Texas. It's happening here and there. But I would think we're not far from a breaking point. If the interstate highway, even 10% of it, can't be crossed because of warping, then trucks, ambulances, chemical companies, things that we need, electric companies, if people can't get to the places they need to go to, then even the work that you're doing is hard to do because you can't get there. You can't get to the places that are going to build these solutions. And the weird thing to me, again, is that when I look at issues and I research, I don't see there are issues like that that seem to be extremely pertinent. It might be buried in a short New Yorker article from a few years ago, but it's compelling. The New Yorker this week had something about phosphate. He said phosphate is, of course, the key fertilizer. There's very little on Earth. It only can be found in Mexico. No, Morocco.
Yeah.
And it'll soon be gone. And so without phosphate, we can't grow vegetables because the nutrients that the plants make are in the vegetables. We harvest the vegetables. They need fertilizer. Fertilizer is phosphate. And where is it? A single mine in Mexico is 80% of it. And it's going to last 5 years. There's so many issues like that that you just don't read about, and so I'm concerned that is there any way to think about this issue?
Yeah, so the question was in the interest of the virtual audience, and I'll paraphrase a little bit, is are there issues that are not getting so much prominence, but immediate urgent issues which needs to be looked at? And is anybody looking at that? So absolutely, I mean, one thing is when I think about climate and try to answer it from there are a lot of answers I could give on that one. But when I think broadly of climate, so a couple of things really worries me. One is on the broader side of things, tipping points. So we get warming, ice starts to melt in the Arctic, more ice melts, maybe there are these methane stores, repositories out there which are much worse greenhouse gases than carbon dioxide and things, and suddenly we are talking about it's a low probability event, but it's very high consequence, and risk is probability times consequence, so it's as high risk. And there are many things like that. This is just one example, but many things like that. Tipping points worry me a lot. That's at the broader scale. And then when I get to the details, and I was saying I will not talk about some of those here, but those are some of the things we do. So if we think that climate is going to cause this longer term change in the statistics of weather patterns, what does that do? What does that mean for our emergency management system? For people who died in Kentucky or Tennessee from floods? What does that do for crop mapping, because things are changing in terms of crops? So those are some of the kinds of things we have been working on. Remote sensing, and that is also where, by the way, AI is often very useful. Climate, we have to think of creative ways to validate. But for those things, we don't, because we get validations immediately after. A lot of AI kind of things are useful there. I was also thinking about some of the examples you gave, which for the virtual audience, I'll not repeat right now, but some of the very specific examples, asphalt temperature, things like that. This makes me think of one example from this was a paper by a few scientists, including a professor at MIT, a few years back. So this was about the Hajj pilgrimage that Muslims make to Mecca. And I have never made that. I'm not a Muslim, so I think I cannot go there. But I have heard from my friends and colleagues about the people who go there and how busy things are there. And what that paper was saying, it will be almost if not unhuman, impossible for humans, almost so, to be able to do that if temperatures rise along one set of projections. And imagine, there are people who, this is a fundamental belief system of a significant part of the world's population. And now, because of climate, and it's not just broad climate, it's in that part of the world, things will get so hot. So it's also another kind of tipping point. It may not be the tipping point that changes everything, but it's something that gets beyond, tolerance levels. That's the other kind of thing that worries me. And when you talk about tolerance levels and things, one thing that worries me even more is there are entities that don't have a voice. There was a time when people used to believe in, nature and giving them a voice, personalizing them. We don't do that anymore. That's the side of the story. But who will give a voice to the species in the Amazon, which are so critical for all of us? Who will give a voice to to plants, trees, flora, fauna, animals in Africa? I don't know. And those species might hit their tipping points even sooner in terms of temperature exceeding this much, floods exceeding this much, and they're gone. And then, of course, humans coming in and, in addition to greenhouse gas emissions kind of human activity, other kinds of activity, deforestation, things like that, and that's it. So those are the kinds of things that worries me. And you're absolutely right. We have to be aware of the big problem, and they will be in the news for sometimes understandable reasons. But when we have to solve it, we have to solve it in sometimes at small scales, bits and pieces. There was one paper where I am a co-author. This was written by Professor Sonia Rowland. She's a professor of law here at Northeastern. It's in a law journal where she was saying, I helped a little bit. This was her paper to a legal audience, but where she was saying she deals with regulatory principles under uncertainty. And we met in some workshop like this, and she was saying, you deal with climate, and you talked about uncertainty, I deal with this. Let's come together and chat a little bit. What does it mean to design regulations for climate uncertainty? And one thing that we thought is, in climate we are more and more certain the more aggregate levels we are. Global warming, we are more certain that what will happen in exactly this place over, in exactly this point in time. But actions often need to be taken locally. So global change and local action. And I'm not saying that locally things will not change or globally action cannot be taken. But I'm saying a lot of the things, to sort of agree with your point, are local, small things that we need to take collectively, and they do add up. So maybe cities acting in unison will contribute much more than global organizations, although global organizations can motivate the need for cities acting. So at this point, I'll leave it as that, but that's topic of a longer discussion. Liz?
All right, thank you, Auroop.
I'm sorry we cannot answer my question. Were some questions about green AI, about solar resource, and also about the new ocean high seas protection agreement. But I guess we can do a blog to answer all those questions for the people. And thank you again for your interesting talk. And please attend our next seminar in March 22nd. Our next distinguished speaker, which is the AI head of the World Economic Forum. Thank you again.
Thank you so much, Auroop. Thank you so much.
The Institute for Experiential AI is proud to invite you to our spring seminar series, featuring leading AI experts and researchers sharing cutting-edge ideas. You can expect AI leaders from a broad range of industries sharing perspectives on defining and applying ethical AI in our Distinguished Lecturer Series, and EAI faculty and Northeastern University researchers discussing their AI research in our Expeditions and Experiential AI Series. Registration is required, and the seminars are free to attend. We hope you'll join us for an invigorating spring semester.